you, Chris? We'll do a general thing first because it's the whole process, I think, might be helpful for you to see a question from kind of the start to finish, like a full question.
Okay.
So I'm going to see if I can pick a story that's got most of what we need.
For some reason, I can't even get like the null value.
Right.
I don't even know why I can't do that.
Okay, I'll make up one because there's not that many to get practice. So let's suppose we have a story that we'd like to do a hypothesis test on. That's just, can we prove something statistically, at least, that something is likely to be true? So I'm going to have a story that says something like this. Population 1 is Scotsmen, Scot women. And we find out that 32% of them in a sample of 400 people are overweight. So they took a random sample of 400 adults and probably used a BMI index, and 32% of them were overweight. And there's another population, and I like picking Americans, so in the second one, it's Americans. And 37% of them in a sample of 100 people were overweight.
Only 37?
Only 37. I'm making these numbers up. So in an alternate reality, it was 37%. It's just basically something you have a story to, right? So the person that's collected these this data quite reasonably thinks that this is evidence that Americans are likely to be more overweight than Scots. And the reason the person thought about that is that 37% of Americans are overweight and 32% of Scottish people are overweight. So that seems reasonable. And you might think, well, that's the end of the question. Can't you just say the biggest percentage wins? There's my evidence. Bye-bye. Well, not allowed to do that because we know from experience that when you take a sample of 100 people or 400 people, every time you take that sample, this number changes, right? It varies. Maybe the next time you do it, it's 30%, but it could be 40. What about the Americans? Same thing. Maybe next time you do it, it's 32%, and the next time it's 40. So we don't know, based on this information yet, whether or not these two numbers are different enough to prove that Americans are more overweight than Scottish people. So we create this process called a hypothesis test. This particular one is a hypothesis test that's looking at the difference between two proportions. Now, this process called a hypothesis test is very structured. In other words, pretty much every statistician or scientist that use it do the same thing. And we make it very structured to reduce the likelihood that you can change the way you do it to change the result. So we're not allowing you to change the way you do it. You have to do it this way. So what's the first step? Well, that's the one you were talking about, this thing called the null hypothesis. And the other one's called the alternate hypothesis. Now, the null hypothesis is typically called H0, and the alternate is typically called HA, but sometimes it's called H1, but we'll use HA. And what are these hypotheses I talk about, the null and the alternate? One of them is saying what we think is true, and it's always the alternate. So what do we think? We think that Scots people are less heavy, percentage-wise, than Americans. So the Scots people, being the first population, is called P1, and the Americans, being the second population, we're going to call it P2. And both the null and the alternate are going to use P1 and P2. The null hypothesis is always going to be that the two guys, the two populations are the same. But the way that we make that happen, the way we say that, is by saying this. The proportion of Scots people take away the proportions of American people who are overweight is the number 0. Now, if you think mathematically, isn't that the same thing as saying P1 equals P2? Right? If P1, the proportion of Scots, was the same number as P2, the proportion of Americans, wouldn't the number P1 take away P2 be 0? Right? If they're equal, their difference is 0. You're looking puzzled, Chris.
No, I got that part.
Okay. Now, the alternate hypothesis has 3 flavors. It depends on what you're after. Sometimes you want to prove that the first guy is less than the second. Sometimes it's the first guy is more than the second. And sometimes it's just you want to prove that they're different. In this case, we'll assume that we wanted to prove that the Scottish people are less overweight than the Americans. You still use P1 take away P2, but you use less than 0. That mathematically is the same thing as saying P1 is less than P2. Right? Scots guys, less overweight than American guys. And that's step 1. You set up the null and alternate. The null in these questions is always going to be P1 take away P2 equals 0. The alternate has 3 flavors. That's the one that we're doing in this story. The other 2 would be that. Now, if this was the case, wouldn't that mean the proportion in population 1 is bigger than 2? And the third possibility is that they're just different. So the difference between them is 0. Now, a couple of wee awkward bits.
Is that how we type it into WebAssign P1
You beat me
minus
to
P2?
it. I was going to tell you that, yes, but it's a little bit trickier than you think. Let's do the not equal to. That's just weird. Evidently, WebAssign doesn't have a not equal to button, so you do exclamation mark equals when you want to do a not equals, and it tells you that in the instructions. Now, the harder one is this fella. A lot of people write that down because it looks right, but in fact, that's a subscript. So what you do is you hit P, and then you go over to that little thingy here, and there's a guy called function. You know, when you hit a box, you get this little math palette. When you hit function, you pick the guy up there, and I think he looks something like this. And so you press that guy, you get P1, take away P2, and then do what you need to do. So what happens, I've seen a lot of people send me emails, and they've written down that. And it didn't work. And they've written down that, and it didn't work. And I'm going to have to make my P's little P's. Don't type capital P's. It doesn't like them. So they have to be little P's. Don't do a normal one beside them. Do a subscript one beside them. So that's just the nitty-picky of WebAssign ain't that bright. It's not a human being. You know, we can interpret things a little bit easier than a machine. The machine needs it to be written in a way that it can understand it, and that's how it gets around it. So that's a little side issue, basically, just so how you can type these in. Phase one is over. Step one is over. The second one, they skip a few times. So you won't get this step two in all the homework questions. But essentially, you should check that you are, in fact, even allowed to do a hypothesis test. So there are certain things that have to be true in your information, the way you collected it and how big it is and so on and so forth. And if it doesn't satisfy these conditions, you shouldn't even try and do a hypothesis test, because you might get numbers, but there's no guarantee that they're telling you the truth. So first thing, in no particular order, is that your samples should be random samples, right? So if you were picking, Scottish people, 400 people, it should be pretty much random, right? You get, old Scots people, young Scots girls, whatever it is, a bit of everything, right? If it wasn't random, could you imagine that you could just be lazy and, I don't know, go to a buffet restaurant, if they still have buffet restaurants, and just ask the people going in, right? Or go to a gym, find a lot of healthy people. That would not be a good sample, because that wouldn't be representative of all Scots people or Americans. So random sample, pretty much, I don't think there's a question where it was never random, but we should be aware that that's true. The information should be unbiased. Right. This particular question would be hard to make it biased, but I can imagine other questions like, are you in favor of abortion, right? Where you phrase the question in a way that's going to make people want to answer it in a particular way, right? The person that's asking is actually quite interesting. Just thought, if a person of color was asking you questions about, do you think America is more racist than it used to be? Can you imagine that the response trees might be different if the person who was asking that question was a person of color, or if it was a white person that was asking that same question? Because there is a possibility there that people will feel obliged, even if they're not aware of it, to answer the question more in one way than the other. So you can have biasness in the person that's asking, you can have biasness in the way you ask it, you can have all sorts of ways of biasing it. In fact, there's a whole chapter about it, wasn't there? About all the things you can do to screw up your data. So, third one is the size of your sample. And we use what I call the 10 rule. That's my name for it. Basically, did at least 10 people say yes to the I'm overweight? Did at least 10 people say yes, say no to that in each of your samples? What that looks like is something like this. NP1 greater than 10, N1 minus P1 greater than or equal to 10, N2 P2 greater than or equal to 10, and N2 1 minus P2 greater than or equal to 10. And technically I should be putting hats on these because we don't know the true values, right? So in this story here, if you do a quick calculation, would you agree that 32% of 400 people is definitely bigger than 10 people? It's more than 10. Would you also agree the ones that aren't overweight, which is the other 68%, is also more than 10? And the same is true for this population. That happens. I'm trying to remember the homework questions. Everybody passes that. I don't think I've got a homework question where this isn't true. But you have to be aware that sometimes that can happen. Let's be silly. It wouldn't be a good idea for me to pick 6 Scotsmen and 3 Americans and try and do a hypothesis test on it. Would you agree that 6 Scots and 3 Americans are just far too many people to even want to risk making any conclusions? So the 10 rule is just a way of us keeping things honest, right? Having at least enough people that you know that you can do an analysis with. Right, any questions about step 2? That you don't always get asked things about step 2 in homework, but they are there occasionally. Are anybody allowed to ask any question? Obviously, at any time. Yeah.
About step 1, sometimes you get like 81 people out of 93.
Yeah.
Stuff like that instead of percentages.
Yes.
How do you write those as like the null hypothesis?
You don't pay any blinking attention to it. That the null hypothesis doesn't care about the way the numbers are written. It's still going to be these two. The numbers that you're interested in happen in step 3, where you actually go to SALT, because SALT's going to take all this information and calculate what's called a test statistic and a p-value. So sometimes they'll tell you 82 out of 400 were overweight and 17 over 120 were overweight. You know, that's fine. Sometimes they'll tell you it's 32% and 37%. That's fine. It really, that doesn't affect the null hypothesis, because what you're saying is they're equal, or the first guy's less than the second. And the first guy is less than the second could be percentage less or number of people less. It's still less, because what you're doing is you're estimating the entire population. So as a proportion, at least. So let's show you step 3. Step 3 is basically, I guess I should put the word, use SALT to find what they call test statistic. I would call it, because it is, the Z-score. And the other thing you're going to use SALT to get, much more importantly, is the p-value, which both of us call p-value, so we don't even have another name for that one. Now, basically, the test statistic is going to use this information, and it's going to give you a Z-score for the likelihood of that happening. And then the p-value is going to tell you the probability that this happened. Right? So that's what their job is. Test statistic is basically just a number that allows us to get the p-value. So if you never told me the test statistic, I wouldn't be too worried about it, but you better tell me the p-value, because that is very important. So what I'm now going to do is jump over to the homework and show you for the story that we've got. Oh, take it back. Too quick for my own good. You kind of touched on this a minute ago when, Chris, you were talking about sometimes it's 32% and sometimes it's, 48 people out of 200, what do we do about it? Well, I should fix this data. I should fix it so I can use it in SALT. In this particular story, Scotsman was that, right? Americans is that. But we need this information to be written as people out of 400. So 32% of 400, 0.32 times 400, ends up being 128 Scotsmen out of 400 were overweight. Are you happy about how the 32 became a number? Now, the 37 one's kind of easy. 37 out of 100 is what 37%. And we need the information written in this format to be able to use salt. You can't use percentages in salt, even if you figured some way kind of pretending you could. I don't know what you'd get, but it wouldn't be right. Right? So you need to use the 128 and 400. So I'm now going to go as I promised, and we're going to look at that fella. Hopefully. Okay. Are you looking at the homework?
Yes.
Okay, let's hit the salt button. Inferential statistics is the tab that you should use in hypothesis testing. This box here, pick a 2 sample proportion, because our story was about 2 distinct populations. The number of successes for 1, the Scots people. That's why I needed 128 out of 400. You see, I needed the out of version. Now, the Americans are coming next, and they are 37 out of 100. We do that. So I'm going to kind of copy down what that looks like so that when you look at the notes physically, at least. So if you bear with me for a few moments, it will remind you what we are looking at. So you choose 2 sample proportion. And then for sample 1, you pick 128 out of 400. Sample number 2, you pick 37 out of 100. So far, so good. Now, you see that little guy says hypothesis test? Make sure that one's got the little dot in it, because that's what we're looking for. Now, in this box, it's called hypothesis, God, that's a hard word to say, hypothesized difference. In the stories that we're dealing with, that is 0. That is basically P1 take away P2 equals 0. But I guess it'd be nice if you actually could type it that way, but that's not the way it works, right? You have to do it that way. So when you're doing a difference in 2 proportions, the hypothesized difference is always 0. You're always going to make the assumption that they're the same. If you go on and do some statistics, a little bit more advanced statistics, you can actually make that another number. You can say that, and the hypothesis is that the difference is 10%, and then you can go and say, I wonder if it's more than 10 or less than 10, you know, that kind of test. But pretend I never said that. We're just going zeros every time. Now, in our story, wasn't our null hypothesis that it was less than? So although that might not look like H naught P1 take away P2 equals 0, and HA P1 take away P2 is less than 0, that's how you type it into SALT, right? It's kind of cryptic, right? That's basically your null hypothesis. That's the cryptic version of what you write for your alternate. So if the next question you're doing is a bigger than, right? P1 minus P2 is greater than 0, right? A bigger than story. Won't you just make that more than? And if you get the, is it different in some way story, won't you make that one not equal to? That's the 3 versions. Now, I should be ready, and I'm going to hit generate results. And they tell you all sorts of stuff. The cool thing is, do you see that the null and alternate now look much more like the way we wrote it down in paper? So that's a backup to, yep, I picked the right one. Because if my null and alternate don't look like that, then I got to say, oops, I forgot, I should have changed this or I should have changed that, right? You can figure that out. Now, they tell you all sorts of things that you don't necessarily need to know. But here is your test statistic. what I call the well, not just me, what most people call the Z-score. And it's okay, the Z-score can be all sorts of numbers. I'm going to round it off because I don't want to write everybody to 2 decimal places, negative 0.95. Can you remember when we did Z-scores a way back in the day? You remember the normal distribution, 0 in the middle, that was where the average Z-score would be, and then it was 1, 2, 3, minus 1, 2, 3. Can you see that numbers, Z-scores, are a kind of reflection on how unusual a particular set of data is? For instance, if you got data and the Z-score was 3, wouldn't you be saying, oh, outlier, weird? Right. Now, in this case, negative 0.95. We're now going to have a p-value. And the p-value, thankfully, is called p-value. And it's 0.17078. Now return. Are you comfortable about how we put the information into SALT for the hypothesis test? Are you comfortable about the null hypothesis, in this case, a less than? And then you hit generate results, and these are the guys that you get. Right, lots of nods. I like nods, so we feel comfortable about just moving on.
Professor, I
Yes.
have a question.
Yes.
Is a way to check for outliers, I guess, with one of the Z-scores or T-scores? Because you said if you saw like a higher value, like 3, you would be like, oh, there's an outlier. Because
Yeah.
go ahead.
Sorry. No, I
No.
cut you off. You were going to finish your thought. Yes.
I had a difficult time in the past, like kind of understanding, I guess, how to determine what an outlier was. So on SALT, like when they show you the graphs, it's kind of clear to see when they do that, oh, there's an outlier, it's way out there. But I never understood like the mathematical aspect of it or the formula. So I didn't know if that's where it came into play or not.
It does. What we look at is when you have millions of data points, like Washington State ages or something, you might not see a gap at the tail end because there's always a couple of people, no matter how old you go, right? So the nice, clear, simple picture is a lot of data, huge gap, sticking out like a sore thumb, and they're great. I mean, I'm not faulting them. They're great because you can see them. What we've discovered is that you have to analyze it a kind of objectively, and that's what Z-scores do. And essentially, we just have a rule. Right? We all agree if a Z-score for a particular data point is bigger than 3, that guy's an outlier.
Okay.
Or less than negative 3. And remember those weird things called interquartile ranges and Q1s and Q3s? There was a thing called the upper fence and the lower fence.
Mm-hmm.
Right. And what they were doing is that was just another way of describing who an outlier is. In the hypothesis test world, which is what we're in right now, these Z-scores are reflecting a very similar kind of thing. I wouldn't use the word so much outlier now because it is only one sample, but it's a sample from a population. And what we're saying is, whoa, that's kind of unlikely harm, that kind of Z-score. And so that's actually where the evidence that we're going to use in step 4 comes from.
Okay.
That's so unlikely that it probably means that the null hypothesis is wrong. And what we think is true is it really is true.
Okay. Thank you very much.
You are welcome. So let us return to this kind of basic question and go to our final step. And step 4 is we use, I'll call it the test, to make a conclusion or a decision, whatever you want to phrase it. Right. There's an extra guy that I've just realized I haven't talked about yet, so I'm now going to talk about it. Whenever you do a hypothesis test, like this story here, right at the beginning, you have to decide on what's called a significance level. And this is called alpha. And it's typically going to be 1%, 5%, or 10%. And that's the most common significance levels that you would see being used in science. So let's do a significance level of, say, 0.10, right? So what that does, it says, if this sample is so rare, so unusual, how unusual is unusual? Well, if it's less than 10%, we consider that evidence that Americans are heavier than Scots. Right? If I make a significance level of 1%, then isn't that a bigger hurdle to jump? You've got to get some data that could only happen by chance less than 1% of the time. So, what does the tip?
Oh,
Yeah.
sorry. On salt, if an alpha level isn't specified, like in the directions,
We
should we
pick it as
assume?
5%.
Okay, I didn't know if
Just-
that was just like an indication that it like wasn't maybe necessary for that problem, or if we should just assume it was 5.
It might be, but we still need a number, even though
Yeah,
it's
that's
not
why I wanted to
necessary.
make sure I wasn't psyching myself out or anything.
No,
Okay.
they really should give you a number, but I know they don't. They should, but they don't always do. So our question, right, our test is the p-value less than the significance level alpha? Now, the p-value that we got was 0.17078, and we're asked to test it against a significance level of 10%. This particular one, would you agree the answer is no? That is not less than that, right? It's no. When the answer is no, right, your conclusion is written kind of like a lawyer. There is not enough evidence to reject it. To reject H0. It can also be phrased as there is not enough evidence to reject the null hypothesis. If we do a test, right, we do a collect data and we come up with some interesting information and we find the p-value of it happening. If that p-value is not significantly small, it has to be tiny. The logic goes like this. We're assuming that there isn't any difference. So what's the chances that you got one? Well, with this sample, that could happen about 17% of the time. That's not particularly small. That could easily happen. When this p-value is small, right, when we say yes to this, then we can say the other conclusion. So can we pretend in a different world this number wasn't 0.17, but 0.02 or something, right? When you say yes to that question, your conclusion becomes this. There is enough evidence. I mean, it's almost the same sentence, right? You just take out the word not. There is enough evidence to reject H0. And that's probably what you would get in one of those drop-down choice menu things, you know, that don't work. But really, they should have gave you the full sentence. I guess they chose not to. And the full sentence would be, there is enough evidence to reject H0. And so, HA is true. Because when you reject the null, you're also at the same time accepting that the other one has to be true. There's only two things that can be true. It's either the null hypothesis or it's the other guy. And if we've kind of proved that it's not the null, logic says the other guy must be true. And that's how we That's basically how we would do from start to finish a hypothesis test. Pretty much the vast majority of questions in 12C are like that, right? They have a story, and then there's a whole load of stuff. Now, they might not have step 2 in it. They might not even have step 1 in it. You know, sometimes they just give you a table, you know, and the numbers are in front of you. So you basically go, well, you probably have step 1. I take that back, but you might not have step 3 in it or whatever. You might just have the beginning and the end. You know, here's a question. What's your conclusion? You know, that kind of thing, where you don't need to go through every step, even though you kind of should, even if they never ask you to, because it's just good math to do it that way. Any questions about that?
No, thank you.
Sorry,
Okay.
you might be leading into it, but I had a trouble with the question asking for the confidence interval. It even gave us the lower limit, and I was like baffled. I couldn't.
Perfect time, Alice, because I'm now going to do that. I wasn't leading into that, but I should have.
Okay.
So they add in some questions. Is it about 2 questions? I don't think it's all of them. It's 2 or 3 at most.
I think I only had 1, honestly, but
1.
I don't.
Okay. Right. So they talk about, I want to get the right word. Is it a one-sided confidence interval or a lower side? What was its wording? No,
Let me check. I have it.
I believe it's one-sided.
Yeah.
Right. So it's a one-sided, and it'll be a 90, a 95, or a 99. 95?
It was 95.
Okay. So they talk about a one-sided 95% confidence interval. Now, we know what normal confidence intervals look like because they have a start and a finish number. You might not have thought the one-sided was that important, but it actually is. Right?
Okay.
So what I'm going to do is I'm going to stop sharing this guy, and we're going to go back into the SALT guy because we have all the information, and I'm going to do it for that Scottish one, right? Well, Scottish and American one, right? Now, yeah, remember the Scots guy, the 128 Scotsmen, 37 Americans, right? Do you notice that there's another little fella here called confidence interval?
Mhm.
Now, if you click on that one, oh, and you choose 95%, which it already did, this is going to disappear, and watch what happens instead. You get a lower limit and you get your upper limit. And the temptation would be simply just to write down, I'm going to round these numbers off. So 0.05 is, I'm scanning the wrong place. Negative 0.16 is one side, and positive 0.0556 is the other side. And I'm now going to go back because that's where you get your information. But that's not the answer.
Yeah, I kept trying to input that information because it gave us one of the lower limits, and I kept trying to, you know, you subtract instead of add because that would have given me the lower limit to test, you know, if I had my equation right. And I couldn't even get close with SALT, doing it by hand, everything. I didn't know what I was doing wrong.
Well, it's this extra bit. That's the lower limit. There's your upper limit. Basically, you're only using one side. But why all the way to 1? Why not? Why is it not 0.5 or 0.8 or some other weird number you don't know about? And why is it just 1 and always 1 in this case? What you're basically doing is you're saying, what's the chances that the difference between them is a certain number? And the 95% confidence interval starts at negative 0.16. What's the biggest difference you could ever get between 2 proportions? Well, since the proportions are numbers between 0 and 1, and so is the other one, can you imagine that the biggest difference you could get would typically be 1? One of them didn't have anybody, right? And the other one had everybody, right? A 0 and a 1. And so that one's fixed. That's just always 1. So in the one that you're doing, I don't know what the number is, but I'll pretend it was 0.123 and you finish at 1. That's all you need to do.
So if it's one-sided, despite it being like 95, 90, whatever percent confidence level, it's going to be 1 for whatever value they don't give you. Okay.
Yes. And if they take away that, then it's the guy that it's always been.
Okay. What, I
Now,
guess,
you can
I'm sorry.
interpret this. Yeah.
what is, I
This-
guess, the reasoning again for going to 1 instead of just, I guess, 0? Because when I hear one-sided, I think of like looking at the bell curvature and then it only being on one
Right.
side, either a positive or a negative, I guess, if that makes
Right.
sense.
Well, if you're looking at a normal single population, it would be what, 0 to 1, right? Nobody got the disease, everybody got the disease, and whatever the chances are. But we're not looking at 1, we're actually looking at the difference between two proportions.
Okay.
Now, the lower limit, we have a number for that, so I don't really need to worry about what that is, right? What's the smallest this could ever be? The answer is that. But what's the biggest this could ever be? Well, the biggest this could ever be would be when that is 1 and this is 0. If you pick, remember these are both numbers between 0 and 1, right? If I said to you P1 was a number between 0 and 1, and I told you that P2 was a number between 0 and 1, then the difference between them, the biggest the difference could ever be is 1.
I understand now. When you said they could only be between 0 and 1, that's kind of when it clicked, because I was kind of confused why you wouldn't have just chosen any other value, but that makes total sense.
Okay, so, and the other rule, a little bit easier, is when you do one of these guys, that number's 1, right? Just because of the
Thank you.
logic of it. Now, we can actually make a conclusion based on this. I know we did a hypothesis test, but since this represents the difference between two proportions, doesn't it contain 0? And if an interval contains 0, does it not mean that because some numbers are positive and some numbers are negative, right? Because it contains 0. Does it not mean that the difference could be either way around? And that's why there was no evidence here to support the argument that Scottish people actually are less fat than Americans. And can you see the power of doing this test is that if you superficially just looked at that data and didn't do anything else, can you come up with a conclusion that ended up not being really valid? Oh yeah, that's guaranteed to prove Americans are fatter than Scots people, or Scots people are skinnier than Americans, whatever way you want to phrase it. Are we good with that? That was a good question.